Welcome back, Physics 30. This is Unit 1F, Part 3 booklet, and it pertains to page 131 to 137 of the duotang. And for Newton's laws, in this part, we're going to be looking at predicting the acceleration of an object given the direction of the unbalanced force, predict the direction of the unbalanced force acting on an object given the direction of the acceleration, so vice versa. Okay? So first of all, what will an unbalanced force do to an object? So if we do have a resultant force, that means that there will be a particular force working in a particular direction, and that means that the object will accelerate. If there's a constant force on something, there is an acceleration in the direction of the force. So as we can see, how are acceleration and force related? So if you increase the force, obviously you increase the acceleration, vice versa. Mass and acceleration, they're directly related to. So back here actually, we would say that F is directly related to A. The larger the A, the larger the force. Whereas mass, if you increase the mass, you'll decrease the acceleration if we have a constant force being applied. So A, we say, is directly related to 1 over m. Okay? Large mass means small acceleration, or small mass means large acceleration. And to relate both of those together, we have what is referred to as Newton's second law. F net is equal to m times A. The net force is equal to mass times acceleration. And of course, mass is in kilograms, A is in meters per second squared. So the unit is kind of weird. Kilogram meters per second squared. Quite often that's shortened to be the Newton. So 1 kilogram meter per second squared is equivalent to 1 Newton. So when we have 1 kilogram accelerating at 1 meters per second squared, there must be a 1 Newton force being exerted on it. So Newton's second law is just that equation basically. We could state it in terms of A, so divide each side by m, and we get A is equal to F net over m. Acceleration is directly related to force, the net force, and inversely related to mass. Or we can simply say F net is equal to mass times A. Okay, and of course there's tons of examples dealing with this in the booklet. I'm going to go through a few here. The net force on and of course we have F net and A being vectors, and of course mass is a scalar quantity. There's no direction. A net force on a 5 kilogram ball is 20 newtons, and I just put a plus in front of that, indicating that it's in the positive direction. What's the acceleration? So easily enough here, 5 kilograms plus 20.0 newtons. Looking for A, just rearrange the equation to solve for A. Now what you may wish to do is, so when you put that in, of course we have plus 20 newtons over 5 kilograms. You may want to revert back and refer to a newton as being a kilogram meter per second squared. That way we can cancel out the units appropriately. Kilograms and kilograms cancel, and we're left with the unit that we're commonly used to using for acceleration, plus 4.00 meters per second squared. Okay, if you're looking at this one, a baseball is hit by a bat with an average force of plus 1,000 newtons, and that decimal place is there, if you recall, just so that there's 4 sig figs. Accelerates at plus 4.00 times 10 to the 3 meters per second squared. What's the ball's mass? So here's all the information we have. We know the net force, we know A and M. Now, I made this note up here indicating that technically, to figure out F net, we look at all the applied forces and the friction force. If we're told nothing about friction, we can just assume that friction is 0, therefore the net force is equal to all of the applied forces. So when it says here a baseball is hit with an average force of 1,000, we're told nothing about friction, so we just assume it's negligible and it's 0, therefore net force equals the applied force here. Okay, so that's kind of an aside there. So rearranging the equation to solve for m. So divide by A, F net over A equals m. And again, change the newtons into kilogram meters per second squared. Meters per second squared cancel on top and bottom, and you'll see that we'll be left with kilograms, 0.250 kilograms. 6. How much applied force is needed to accelerate a 2 kilogram block of wood at plus 4.00 meters per second squared along a rough table against a 10 Newton force of friction? Now, I put that negative in front because friction is always working against you. So if we're moving in the positive direction, that force has to be negative if it's friction. So we know mass, we know A, we know force of friction, and we're asked to find force applied. So if we know mass and if we know acceleration, we can figure out the net force being applied. So F net equals MA, 2.00 kilograms times plus 4.00 meters per second squared. That gives us plus 8 kilogram meters per second squared. And of course that is the same thing as 8 newtons in the positive direction. And now we're asked to find FA. So we now know F net, the overall resulting force should be that. The force of friction is 10. Be sure you put a negative in front of there because friction's working against you. So to solve for FA, it's F plus negative 10 or F minus 10. So to move that 10 to the other side or to isolate FA, add 10. This cancels, and the net force must be 18. And that makes sense because if we want to result in 8 newtons, and if we have friction is 10, this number here would have to be 18 because 18 minus 10 gives us 8. And again, don't forget the negative on the force unit. Okay, let's see here. A jet plane. A jet plane pilot decides to accelerate horizontally. If the thrust of the engine is increased to plus 50,000 newtons at a time when air resistance acting on the 4,000 kilogram plane amounts to negative 30,000 newtons, what's the plane's acceleration? Pause the video, see if you can figure it out. It's kind of like this question here reversed. Okay, so pause it, write down the variables that you know, and see if you can plan it out. Okay, if you had a time to look at that, first thing you need to do is always write down what the information that you're given. Plus 50,000 newtons. The mass is 4,000 kilograms. Force of friction is negative 30,000, and we're looking for A. To find A, we need to know mass, which we do. We need to know the net force. We don't, but we can easily get it from the information that we're given. We know that we're applying a force of 50,000. There's 30,000 newtons of drag or friction, so the net force is 20,000. Then it's easy. Solving for A. And again, I put 20,000 newtons in the form of 20,000 kilogram meters per second squared. Kilograms cancel, and I'm left with plus 5.000 meters per second squared. Okay, I have another side here. Calculate the, and I think that's it. This is the last page, so we'll quickly go through it here. Calculate the unbalanced force on a 4,000 kilogram truck that changes its velocity from 22 meters per second to 8 meters per second. So the plan of attack here, we're looking for the force. We know the mass. We're looking for A. We don't know A, but hey, back in previous unit, we had acceleration is equal to final velocity minus initial velocity. So yes, you may have to use some equations from earlier on. Initially going 22.0, end up going 8.00 meters per second in a time of 3.5. So you know that our velocity here is slowing down, which means we must be decelerating or negative acceleration. 8 minus 22 over 3.5, negative 4.0 meters per second squared. So looking at this, 4,000 kilograms times our negative 4.00 meters per second squared. So you can see here I get negative 16,000 kilogram meters per second squared, or newtons. There's 3 sig figs here, so 1, 2, 3. Put a line over that 0 there indicating that those 3 are significant. So the truck is slowing down, so obviously there's a net force that's operating against us, i.e. the brake being applied on the truck, and that net force, of course, is negative because we're slowing down. Okay. Next, how long does it take a 50-kilogram rider on a 10-kilogram bike to go from rest to 4 meters per second if the unbalanced force is 48 newtons? So we're looking for time here. And we know the mass, the total mass here, it's the rider and the bike. So it's 60 kilograms. Initial velocity is 0. We end up going 4. And net force is that. So the rationale here is we know net force, we know mass, we can get acceleration. Then using that equation that we used previously, interchange A and T, and we'll be able to solve for T. So first of all, solving for A, F net divided by M, represent 48 newtons as 48 kilogram meters per second squared. Kilograms cancel, and I'm left with plus 0.800 meters per second squared. And then from there, notice how I rearrange this. Just solve for T, multiply by T, divided by A, etc., or just think of it as interchanging. Final velocity minus initial velocity over that A, and that works out to be 5.0 meters per second squared. 10. What is the final velocity of a 150 kilogram motorcycle driven by a 50 kilogram rider if it goes from rest and it's going for 11 seconds? Unbalanced force is 8 newtons. How do we figure out V final? So the total mass here is the rider and the bike. Initially doing that. So we're looking for V final. We know T, we know I, so we'll be using this equation here to get V final. And the only thing we don't know is A. So to figure out A, we know F net and mass, so we can figure out A that way, and then it's easy. So the net force, 800 newtons, or 800 kilogram meters per second squared, divided by the mass of 200. So I get 4.0 meters per second squared. And then we had a different way of rearranging that equation. If we're solving for VF, V initial plus A times delta T. So we have 0 plus 4 times 11. And we get 44.0 meters per second. And earlier it was stated that that is in the south direction. Okay? So Newton's second law, F net equals ma. And a few other equations we could use are the acceleration equations, or the different form of the acceleration they've rearranged. And also we looked at this, the net force. If there is friction involved, we have to be aware of that. If there's no friction involved, it's just simply F net equals Fa. Okay? We'll see you later.